Is it possible that the entire Earth has undergone catastrophic upheavals in the recent geological past? Upheavals that might have profoundly affected not only the planetary environment, but human civilization as well. New, compelling evidence and research has just recently been published supporting and confirming that a catastrophe of global proportions did indeed occur in the recent history of the Earth at the time of the Younger Dryas boundary around 12,800 years ago. What could have been the cause of this event? This new evidence expands the geographic range of this planetary cataclysm and supports the hypothesis of a cosmic impact from space. Is it possible such an event could occur again? And if it did, how would it affect modern human societies? I'm Randall Carlson, and I'm inviting you to join us for another episode of the Squaring the Circle podcast. Well, hello everyone. Here we are again, about to embark on another journey of exploration and learning. And to join me in this endeavor will be my friend and colleague, John Arthur Fiallo. Hello, John. Good to see you again. I'm doing well.
Good to see you. Doing well over here, too.
Okay. Yep. So, so two new papers have come out with evidence for an impact event right at the lower Younger Dryas boundary, which dates to right around between 12,800 and 12,900 years ago. And one of these areas, one of these regions that yielded up evidence for a cosmic impact is in the state of Louisiana, not too far from where I once lived. And the other one was in the Baltic region of Eastern Russia. So I thought maybe we would start by just giving a little bit of insight into the Younger Dryas events. And one of the early indications that something happened at this time period around 12,900 years ago, give or take a century, is this mysterious layer called the black mat. The black mat is a horizon that is dated to right around 12,900 years. And it seems like it's a demarcation zone that is correlated with major climatic changes. And it also seems to be correlated with the final demise of a lot of the great megafauna species that inhabited the Earth for many, many thousands, 100,000s, even in some cases millions of years, that all seem to disappear from the Earth around the same time, roughly with the end of the last ice age, from about 14,000 to about 12,000 years ago. But it seems that there was a major spike of megafaunal extinctions that occurred pretty much right on top of the Younger Dryas boundary, so that a lot of species that somehow managed to survive up to that black mat horizon, their fossil evidence was found below, but not above the horizon. So, were you able to find some interesting pictures showing the? So people can see what we're talking about. I have a few here. I could.
So while you're pulling those up, I actually have a set of locations prepped where these black mats have been found in the contiguous 48 states and in Canada. And so if you're on audio, I do apologize. This podcast will be worth looking up on YouTube or Rumble, but you can see quite a few different areas where they've taken core samples, or you can see it, in a carve out in a canyon or in caves where there's this black mat.
Yeah. Now this, I need to point out that not all of these sites have impact proxies, but a significant percentage of them do. It's also been contested that the black mat sites are not exclusively celestial or cosmic in origin. But what they do seem to indicate is a very concentrated period of climatic change and the formation of these carbon-rich layers.
And before you go too much further, what is an impact proxy for those who are just tuning in now?
Well, an impact proxy, when you don't have the direct results or the direct evidence of an impact, such as eyewitness accounts or very obvious evidence, such as an impact crater, along the lines of the famous meteor crater in Arizona. And the crater in Arizona is the result of a direct impact of an iron metallic asteroid into the Earth somewhere around 50,000 years ago. However, when you have an impact like that, it creates a highly energetic, high temperature, high pressure environment. And this environment can produce things that only occur under very extreme or unusual circumstances. And over the years, many of these now have been correlated or connected with known impact events. And amongst these, and we're going to be looking at those somewhat in this episode, microspherules. That is one of the proxies. We call it a proxy because it's a secondary effect, but it's a secondary effect that is produced by phenomena that would support the conclusion of some high energy, high temperature, high pressure phenomena, most likely impacts. And in fact, some of the temperatures produced that are indicated by the melting of material that's necessary to produce these the spherules, for example, is extremely high, up in the range of 2,500 to 3,000 degrees centigrade. So that's extremely hot. So then the question becomes, under what conditions is it possible to have temperatures in that temperature range? And the answer is the two things we mainly know, which is cosmic impacts and nuclear weapons explosions, like the atomic bomb explosions, say at Trinity, produced effects that are very similar to, in some regard, to the effects of a cosmic impact.
So kind of like the sprawl that you would see at a blacksmith. When you're hammering or forging something, you'll have metal sprawl or glass sprawl, etc.
Yeah. Now, there are chemical proxies, such as platinum. Iridium is a very typical one. Osmium. These are the platinum group metals. And it was iridium that was first indication that the dinosaur boundary of 66 million years ago, the Cretaceous Paleogene, as it's now called. It used to be called the Cretaceous Tertiary, but now it's called the Cretaceous Paleogene. That is the event horizon at which the dinosaurs disappeared in a geological eye blink. And there are impact proxies there. And the first indication that there was some type of a cosmic event associated with the demise of the dinosaurs was the discovery of the iridium enhancement, or a spike of iridium, precisely at this KT or KPG boundary. And I know there were technical reasons for changing it from Cretaceous KT boundary to KPG, but it sure is a lot easier just to say the KT boundary. So in writing about it, I will use the modern nomenclature, which is K-PG, small case g, but in talking about it, I'm going to refer to it as the KT boundary, because that's how I talked about it for many decades before the nomenclature change. Is that acceptable to you, John?
That's acceptable. Absolutely, Randall.
Okay, so people will know what I'm talking about. And if anybody's out there, any paleontologists or geologists, yes, I do know now that it has been changed from Cretaceous to Cretaceous Paleogene. We don't need to get into the reasons for that right now. But
and let me tease one more question.
Sure.
Why is the presence of iridium so important in a spike? Because iridium is not that level of iridium is indicative of something specific.
I'm going to pause for just a minute to talk about our partners over at Shippo, who may save you a significant amount of headache in your day-to-day business. We sell a variety of geometry tools and models, like our beautiful platonic solids here at Randall Carlson LLC. And when it comes to managing shipping, e-commerce, and returns, we've been using Shippo for over 4 years now, and we're very pleased with their service. Shippo's interface is intuitive, the primary order page is easy to navigate, and we have enjoyed stellar technical support. If Shippo can help you with your needs, please use the code below to partner with a great company while supporting our work here at Squaring the Circle. Thanks, and now back to the show. Right, okay, so iridium is a siderophile, meaning it loves iron. So in the early formation of the Earth, you had iron, which is a high-density material, bonds to the iridium that would have been present in the early crust of the Earth. That iron subsides towards the center of the Earth because it's heavy, it's dense, it sinks, and it drags the iridium with it. So what that does is it leaves a deficiency of iridium in the Earth's crust. However, in primordial objects like asteroids, the iridium is still very abundant, and there are high percentages of it. So if an asteroid strikes the Earth, explodes, vaporizes, it can create a cloud of material that can literally circumnavigate the globe and precipitate out, and the iridium that is in that cloud will then be deposited in the Earth. Now that's what happened at the KT boundary 66 million years ago. And Walter Alvarez and his father, Luis Alvarez, and the rest of their team were looking at an outcrop, the dinosaur killing the outcrop in Italy, not necessarily at that point thinking cosmic catastrophe, cosmic impact. But what they were trying to do was to determine what was the span of time over which this layer was deposited. And so in trying to establish, was it a few years, was it thousands of years, hundreds of thousands of years, that was not known. But it was suggested at this time, which is back like in the 1970s, that the dinosaur killing episode may have been considerably faster than had been previously recognized or considered. And so they were looking to try to determine the duration of this deposit that seemed to be associated all over the world with the top of the Cretaceous, right? The transition from the Cretaceous to the Tertiary. Now, or to the Paleogene, okay? But so important or so profound was this transition that it was not only geological periods, like the Cretaceous period to the Tertiary period, that was shifted. It was also two of the great life eras on Earth, the Mesozoic, which was the era of middle life, and the Cenozoic, which was the era of recent life. So it was apparent already by the 70s that something really significant had happened right there. So they're taking a look at it, trying to determine the duration, and that was when they stumbled across the spike of iridium. And the first thing they knew, and I guess I don't remember who it was on the team, it was probably Luis Alvarez, the, I believe, Nobel Prize-winning physicist, that suggested that iridium was abundant in asteroids. And so what they did was they were thinking, well, could there have been an asteroid impact that in the heat and temperature of the explosion of the impact, could the vapor cloud have encircled the Earth and then precipitated out? But so what they needed was more evidence that this iridium layer was found in other locations around the world. So if memory serves me correctly, they contacted colleagues in Denmark and New Zealand and asked them to go back, take a look at the boundary and analyze it for iridium. And in both cases, yes, they found a very significant iridium spike. which now they had evidence that you had this deposition of iridium both in the northern hemisphere and the southern hemisphere. Additional sites disclosed that pretty much everywhere you looked at the KT boundary, you found enhanced iridium. So this led to the conclusion that there had been a iridium dusting of the entire Earth. Now, based upon the estimates of the amount of iridium that would have taken, so essentially extrapolating from, say, at this point, I don't know, 4, 5, 6 different sites around the world, they were able to assume that it was a fairly uniform deposition of iridium around the entire planet. So from there, they were able to calculate approximately, ballpark, how much iridium that actually was. Then going back to the known composition of meteorites and asteroids and so on, which are basically based on two things, the spectral imagery, which showed the spectral frequency of iridium from asteroids, and actual deposits, associated with meteor craters that are known meteorites, right? That iridium, they had a sense of what the concentration of iridium would be in an asteroid. So then from there, you now calculate how big of an asteroid, given X percentage of iridium, would it take to accomplish this dusting of the whole Earth? And the answer was an asteroid, a stony asteroid or a stony iron asteroid, somewhere in that range of densities of about 6 miles in diameter. And that would be, the size of Mount Everest, and it's flying in, slams into the Earth at 12 to 15 miles per second, maybe faster. That's going to release just inconceivably powerful explosions. The kinetic energy released during an event like that is going to be incomprehensible. And this work was published in 1980. 10 years later, it took a full decade. The critics were going after it, saying, look, maybe, but we're not buying it until you show us a crater. There's got to be a crater on Earth somewhere that dates to that period, and it was not known for early 90s. Finally, it was Petroleum Mexico, Pemex, was drilling in the Yucatan Peninsula looking for hydrocarbon deposits, and they came up with this. They kept their drills kept pulling up this green-colored, glassy, vitreous material. And I think this goes back even to the early 80s when they were doing this, and but nobody was connecting it with cosmic impact. They assumed that it was somehow volcanic or something related, but not impact related. And I forget the exact story. It's been, I haven't refreshed myself on the details of the historical unfolding of this evidence, but there was an American team, I think I can remember his name, I'll think of it in a second, but something led them to take a look at this green glass, and they decided that it was, I think what it was they found the green glass, and the date of that deposition of the glass seemed to fit very closely to the KT boundary. I think that was it. And so they went and they took another look at the evidence, and as they did, what it disclosed and revealed was that there was, in fact, this giant subsurface buried crater under several thousand feet of limestone. And it was of the requisite size because, an object, there's a scaling ratio that you can look at between the size of an impacting object and the width of the crater that it's going to produce. And typically the range is 10 to 20 to 1. So if you've got an object, or even larger than that. So I think in the case of the KT boundary, they concluded that the impact would have to produce a crater about 120 miles in diameter, maybe larger. maybe larger. And that is what it turned out. They're still debating the size of the crater, the Yucatan crater. We're taking a little bit of a detour here to tell a story that I think is going to be valuable. I was coming down the stairs, and I think somebody just ahead of me had spilled a little bit. My foot hit it, slid out from under me, and I tumbled down 3 or 4 stairs to the bottom. I sure banged up my left knee. It was painful, but I was very relieved to remember that I happened to pack my CBD from the gods salve. And I was really grateful that I had remembered to do that. So that night I put some of the salve on, went to bed. Though I've being in the construction and building industry, I've had many falls and injuries and stuff, and I figured I'm going to be laid up with this for a month. We drove home. I think it was 3 to 4 days later. I continued applying the salve, and I would say within a week I was getting around pretty good. I always bring the oil when I travel, and I'm now, after this episode, I'm like, okay, I'm always going to have the salve with me too. But it turned out to be just the required dimensions. And so it's the required dimensions that you would expect for a crater that is produced by the impact of a 6-mile asteroid. It is dated to the time period very precisely now. And you can also see the shock effects of it. It generated a huge tsunami that washed up. And in fact, the area, if you dug down below this new site in Louisiana, by a place called Perkins Lake, which is near Lake Charles, Louisiana, which we'll be looking at in a minute. If you dug down below that, I think it's about a half a mile below, there is a Younger Dryas, not a Younger Dryas, sorry, a Cretaceous Tertiary layer, and it was a tsunami, a giant tsunami layer. And it has been covered over by material, but it's been preserved. There are giant current ripples that were found. And it was from this huge tsunami that washed ashore of Louisiana, made landfall, did its run in, and then flowed back off into the Gulf. And this was recently discovered as well. I wrote something on that, and I might be able to pull that up here in a minute. In fact, I reported on it in one of my recent newsletters. I described the discovery and so on. But the thing that we're going to be talking about near Lake Charles, of course, is much more recent. It is on the surface of the Earth, not buried,
So when looking for the evidence for an impact, you have to look for the crater, if there is one, or for the imprint of an airburst, right?
Yes.
And then we have to look for the proxies or the fallout that would have occurred from that. And that's what these 2 new discoveries really seem to be doing for us today, is they're giving us the fallout and potentially the impact from an airburst. It's not really a crater,
Correct.
But the impact zone from an airburst.
Yeah. I'll also mention one of the very convincing proxies that is associated with the high pressures of an impact are nanodiamonds. And nanodiamonds have been found over and over again at the Younger Dryas boundary. And interestingly, they're very similar to nanodiamonds found at the KT boundary and have been compared to the two. So why don't we talk about a little bit about the background of the Younger Dryas events. Let's see. So going back, let's see, how far should we go back? The Younger Dryas boundary was already a matter of controversy before the famous paper that was published in 2007, first suggesting that the megafaunal extinctions were triggered by a cosmic impact, right? So, like, here's a paper that was published in 1989, right? It was entitled "A 17,000-Year glacio-eustatic sea level record. Now, what do I mean? What is glacio-eustatic? Okay, we've talked about the phenomenon of eustacy or eustatic changes in ocean level. Okay, so we know that the planet is subjected to periods of deep glaciation and in periods of deglaciation, such as we're in now. So glacial epoch, interglacial epoch. There have been many, apparently many glacial epochs. So what happens in a glacial epoch? You've got an enormous accumulation of glacial ice on the surface of the continents. Now, mostly like we see now in Antarctica and Greenland, we have, we have, I think, about between 4.5, 5 million cubic miles of ice over the South Pole. And we have maybe almost 1 million cubic miles on Greenland, right? So now if we go back to the last glacial episode, there was more than double the amount of ice, glacial ice. Well, that glacial ice is part of the hydrosphere. And the hydrosphere is more or less steady state with some tweaking, yes. But it's more or less a consistent state. And it doesn't matter whether it exists in the form of water, vapor, or ice. It's all part of the hydrosphere, right? Well, if you have more glacial ice, it means you have less liquid water, primarily in the ocean basins. So when glaciers grow, sea level declines. When glaciers melt, sea level rises. So this rising and falling of sea levels associated with the expansion and contraction of glaciers that's what's called eustatic sea level change. It's spelled EU static, E-U-S-T-A-T-I-C, eustatic. So in this term here, the title of this article is glacio-eustatic, meaning, again, just to sort of indicate, because we're talking about fluctuations in glacier mass directly correlates with rises and falls of sea level. Then it goes on to say in the title, influence of glacial melting rates on the Younger Dryas event and deep ocean circulation. So in the abstract, it says that coral reefs drilled offshore of Barbados provide the first continuous and detailed record of sea level change during the last deglaciation. The sea level was 121 plus or minus 5 meters below present level. So I'm going to put in, let's just look at what the maximum. That would be 126 meters times 3.28. So that would be 413 feet, right? So if you took out, that's how much of the ocean, the world's oceans, were extracted, precipitated as snowfall out onto the continents that did not melt. Like we now have every year, of course, we have snowfall in the northern hemisphere. Where I grew up in Minnesota, sometimes by the end of the winter season, we'd have 6 feet of snow. But then, as we all waited and anticipated, was the spring thaw, and all that snow would melt away. But now in the onset of a glacial epoch, what's happening is you have the snowfall, but spring doesn't ever come. So the snow doesn't melt, and in the next year there is more snow, and on top of that there'll be more snow, and this will go on for thousands of years until the snow is thousands of feet thick. But as the snow builds up, the weight of the overlying snow compresses the snow. It goes through two phases. It goes from snow to what's called firn, which is FIRN, which is an intermediate phase between the snow that's accumulating on the top of the glacier and the weight that compresses it and transmutes it or transforms it into glacial ice. Okay. So anyways, the abstract goes on to say that the deglacial sea level rise was not monotonic. And this is important. It was being understood already back in 1989. Rather, it was marked by two intervals of rapid rise. Varying rates of meltwater discharge to the North Atlantic surface ocean dramatically affected North Atlantic deep water production and oceanic oxygen isotope chemistry. And a little bit there is that you have light oxygen, oxygen 16, heavy oxygen, oxygen 18. When you have cooling, atmospheric cooling, there'll be less energy available to evaporate ocean water. When you increase the thermal energy, there's more energy to evaporate ocean water. Well, the more energy there is, the more readily it can evaporate the heavier oxygen. It's more effective at evaporating heavier oxygen during warm periods than cold periods when the energy is not as available. And so what happens is that during these transitions, you will have, so if you have a lot of heat energy, evaporates a lot, that vapor that precipitates out is now going to be enriched in oxygen 18, heavy oxygen, right? If it's a colder period, the opposite happens. So those oxygen isotope ratios are preserved in the layers of glacial ice. So you can look at the oxygen isotope ratios, and that's going to tell you about what's going on in the climate. So anyways, this was a study going back to 1989 where they were first realizing that the term they use is monotonic. The rise of sea level wasn't a smooth curve. There was at least two pulses, what they say, two intervals of rapid rise, which have come to be called meltwater pulse 1A and meltwater pulse 1B, right? So at this point, they don't have the detailed dating of this. So let's see, changes in continental ice volume during the last deglaciation generally have been inferred from two direct sources: geological mapping of the retreating ice margin and the marine isotope record. Direct estimates of glacial ice volume based on measured glacio-eustatic sea level changes are well documented from 9,000 years before present, but are poorly constrained from before this time. Ruddiman, who was one of the esteemed scientist who was working on these problems back then, recently reviewed evidence supporting three different deglaciation models. One, the smooth deglaciation model, with the most rapid change centered at 11,000 years before present. Two was the French two-step deglaciation model, with maximum melting rates from 14,000 to 12,000 years before present, and again from 10,000 to 7,000 years before present. So there's this, now these dates have been revised. They're older now than what was given in this paper, okay, in 89. But what this is showing is that you've got this period, 2,000-year period, 14 to 12, and another one from 10 to 7. So you've got this 2,000-year interval separating these two melting episodes where the large volumes of glacial ice are melting and going into the global oceans. So yeah, they were from 14 to 12,000 years, from 10,000 to 7,000 years, separated by a mid-deglacial pause with little or no ice volume loss. So see, this was already being recognized back in the 1980s, okay? And third, a Younger Dryas deglaciation model, which distinguished from the French two-step model, by a mid-deglaciation reversal. Not just a pause, but an actual reversal with significant ice growth in there. And it does look like there was ice growth. It's not our intention to go into that depth in this discussion, but this kind of is setting the stage that there was something that happened in this interval, okay? So Richard Fairbanks, he was professor emeritus of the Earth and Environmental Sciences. He was working on this back then, along with Ruddiman, quoting him. I sought to test the validity of these models, the three ones I just discussed, each with their own important climatic and oceanographic implications, by extending the existing coral reef sea level curve to the last glacial maximum. Because as sea levels go up and down, corals will build their reefs up to keep up with sea levels. When sea levels drop, okay, they can, coral reefs will die off. And then you'll have a replenishment of coral reefs at a lower submarine level. The fossil coral reefs surrounding Barbados are a very good system for examining in detail and the timing of the last deglaciation. Here I show that the sea level curve derived from the Barbados Reef supports the French two-step model. Well, the French two-step model is the one where there was a pause, but not necessarily a reversal. In other words, pause in the melting or disappearance of the ice, but not a regrowth. I then reviewed the evidence for the oceanic and climatic response to this two-step deglaciation, with particular emphasis on understanding the cause of the Younger Dryas event. So then, in the same article, he quotes Wallace Brecker, who also was one of the key scientists working on this stuff back in the 70s and the 80s into the 90s. So Brecker dated the minimum oxygen 18, that's what this delta 18O means, oxygen 18 isotope. The delta is a little sign for the isotope. So this is your heavy oxygen right here. And so this is maximum meltwater discharge in the Gulf of Mexico. This is just the nomenclature for the cores that they took in the Gulf of Mexico. And they were dated 11,840 and 12,000 years before present, which are equivalent in age to accelerator mass spectroscopy, carbon-14 dated, minimum in North Atlantic. Don't worry about that. Here's the key. These two events correspond precisely with meltwater pulse 1A, dated at 12,000 years before present. Brecker et al. Noted that the maximum glacial meltwater discharge from the Mississippi River was followed by minimal discharge between 10,500 and 11,100 years before present. Now, to get the more updated, simply in approximately, and it'll get you close enough, simply add 2,000 years to these dates. So meltwater pulse 1A, which they were dating at 12,000 years before present then, is now dated closer to 14,500 years, 2,500 years. And so then here, this would be 12,500 to 13,000 if you did the updating. And so this period of minimal discharge would have been the Younger Dryas. So independently, this Brecker and his team had noticed that there was a maximum meltwater discharge followed by a minimal discharge of the Mississippi River. Well, that is because the Mississippi River is carrying enormous volumes of meltwater from the melting ice sheets up to the north over Canada. Then he goes on to say, the rapid disintegration of the northern hemisphere ice sheets during meltwater pulse 1A and meltwater pulse 1B must have introduced large volumes of low oxygen 18 meltwater into the North Atlantic during the summer season. The oxygen 18 spiked meltwater has two possible fates: entrainment in the North Atlantic, deep water, or evaporation. Because deep water formation may have been halted briefly during the peak discharge, evaporation of oxygen 18 spiked surface water must have occurred to some extent. Well, now this is, that now one of the concerns is that there could be, because of global warming, et cetera, and the amount of meltwater coming off the Greenland ice sheet is going to interrupt the circulation of the Atlantic circulation. However, comparatively speaking, the volume of the volume of water discharged into the Atlantic Ocean during the melting of the glaciers was way, way beyond the volume of water coming off of the melting glaciers on Greenland. So anyways, the Greenland ice cores from Die 3 and Camp Century are both marked by two distinct oxygen 18 minima during deglaciation. The immediate implications of the Barbados sea level record compel us to reevaluate some of the traditional depictions of the Younger Dryas event. Whether or not the reinterpretations presented here are correct depends on the reliability of correlations between radiocarbon-dated marine and terrestrial signals. My results emphasize the primary role of meltwater discharge rates on the production of North Atlantic deep water and rapid climate change in Western Europe. So already we're seeing that there is these what are called teleconnections between these various events. Now, what I'm going to do is go to the next slide here, and you'll see that here you have the graph that was in the Fairbanks paper, and this dash line represents the first of the models. Let's see, what did they call it? The smooth deglaciation model, with the most rapid change centered at 11,000 years BP. So we go back to here. This dashed line represents the smooth deglaciation. So it starts melting, it accelerates, it peaks right at 11,000, and it tapers off nice and smooth, right? Well, here's the two-step model. So what you've got is you've got a massive spike right here that is dating to right around 12,000 years. Interestingly, they were already getting data that suggested that it was earlier, and that's what the green spike is. So this is actually showing closer to 13, even where it starts right here, you can see it's about 14,500 years ago, right? And then you have this huge spike, and then it tapers off. So this trough would be the Younger Dryas. And then you have this second meltwater spike, meltwater pulse 1b, which is a very rapid rise in sea level. And these are sea level curves that you see right here. Over here, you see the apparent discharge rate in cubic kilometers per year. So you look at this meltwater pulse 1A, you're looking at almost 15,000 cubic kilometers per year of water, meltwater, discharging off the ice sheets. That's a lot of water, okay? And there's nothing similar to that going on right now. Okay, then over here, we've got the plot of terrestrial oxygen 18 records from Greenland ice cores with 6 radiocarbon ages. And it's already beginning to show the two spikes of warming. Here's one warming, and here's another warming, and here's the Younger Dryas in between. And then what you have here is the beginning of the Holocene, where once you're at this stage right here, where my cursor is, the ice sheets, the great ice sheets, are mostly gone and equivalent to what they are today. Now, these are older. The Camp Century and the Dye 3, they're older. We have newer that were published in the early 90s. These were from the 80s, right? The resolution is not as great. The more recent cores are much more precise. So, as it says here, 2 massive meltwater pulses to the world's ocean during the last deglaciation. I would suggest that there's actually a third pulse in here that hasn't shown up because we didn't have the resolution available back in 1989. So that, what is that? That's 36 years ago. So we've got a greater resolution now, and I think that there's evidence that there might be a third meltwater spike in here. So then I'm going to caking it through the evidence that this is 1992. There's still no impact hypothesis in 92. However, what you see happen, large perturbations of ammonium and organic acids content in the summit Greenland ice core. So this is some of the first results. So let me mention that the Camp Century and the Dye site are both near the margins of the ice sheet, of the Greenland ice sheet. So at those margins, the ice is much more dynamic. It's more susceptible to changing, to melting. And so they realized that the glaciologists who were doing these extractions realized that there was going to be that there was going to be some inconclusive evidence in there because of the distortions that occurred in the ice sheet. So what they wanted to do was they wanted to go to where the ice was the most stable and there would be the least amount of deformation. And that was at the summit of the ice sheet, right? It's also going to be the most difficult to drill because it's almost 2 kilometers thick there at the summit of the Greenland ice sheet. But over 5 years, 2 teams were able to pull off these coring efforts, and it was heroic indeed because you only have a few months out of the year that you can actually get up there and to drill. Both teams, I think the European team got to bedrock first, but both teams did get to bedrock. They extracted the ice cores, and those ice cores are still being studied to this day. However, this is what I found very interesting when this article was published back in 1992, because I'm already thinking impact at the Younger Dryas boundary at this point, for other reasons, which we can talk about later. But this was published in the Geophysical Research Letters on March 3rd, 1992, and this is what they found. Biomass burning is influencing the atmospheric chemistry by emitting large amounts of reactive species, such as hydrocarbons, organic acids, and nitrogen compounds. Polar ice cores provide a unique record of precipitation whose chemistry reflects the atmospheric composition at the time of deposition. The analysis of such ice samples, therefore, allows an estimate to be made of the concentration of atmospheric impurities in the past. During the first season of the deep drill operation, to GRIP, the Greenland Ice Sheet Project, at Summit, central Greenland, continuous ammonium measurements were performed between 100 and 600 meters depth, covering the time period from 330 to 25,000 years before present. The NH4 plus concentrations show seasonal variations of 1 to 20 nanograms per gram, with some sporadic high values up to 600 nanograms in narrow layers. The chemical fingerprint, here's the important part. The chemical fingerprint points to biomass burning causing the high ammonium peaks, right? Biomass. So here's a proxy. Biomass burning proxy, one of the proxies for biomass burning is high ammonium peaks. Ammonium will be emitted originally as NH3, whereas the organic acids are emitted directly and are also produced in the atmosphere by oxidation of hydrocarbons. Let's see, okay, so here we go. Additionally, the emissions must occur in such a way that they have the possibility to reach Greenland. Only biomass burning, and more specifically, large forest fires, satisfy the above-mentioned conditions. Plumes from forest fires have enough energy that they can extend to the free troposphere where they can be efficiently transported over large distances. So, the comprehensive study of ammonium perturbations observed in Greenland snow layers have shown that such summer events are characterized by a large increase of several organic species. Such perturbations by 1 or 2 orders of magnitude in the atmospheric content of reactive species may have strongly disturbed the photochemistry of these high latitude regions. So then, let's see. So here we go. Then we present new evidence suggesting that the late glacial worldwide episode of cooling, known as the Younger Dryas, had significant impact on climate, vegetation, and human economy in the southwest. And that is then associated, because this study also points out the possibility of reconstructing past biomass burning events in the northern latitudes, which could have been modulated by past climatic conditions. So already now they're showing that there are changes in climate that are associated with these peaks in large forest fire proxies. And your NH4, as it says down here, that's basically ammonium. So now in the Levant, a new pollen core extracted from Lake Hula and plant remains from the early village of Abu Huraira 1 indicate the forest may give way to steppe in response to drier climatic conditions contemporary with the Younger Dryas. Now, what's interesting is because new studies have been come out in the last few years on Abu Huraira, which suggests that it was the site of an impact. And I think I've got the papers. And in fact, Stephen Collins, who's going to be at the Cosmic Summit, was one of the lead scientists that worked on the studies of impact proxies at Abu Huraira. So going on here, the Pleistocene to Holocene transition in human economy in Southwest Asia, the impact of the Younger Dryas, published in American Antiquity. The Younger Dryas apparently had a profound effect on the environment of Southwest Asia and contributed significantly to the adjustments in human adaptations that resulted in the development of agriculture. So what we're seeing here is a pattern beginning to develop that suggests that the climate had changed drastically. There was meltwater spikes that seemed to be associated with it. And here we go. The Younger Dryas was first recognized in the pollen record of Northern Europe. During the late glacial, as the temperature rose and the glaciers began to retreat, the tundra vegetation was replaced by birch and pine woodland. These trends began during the Bolling and Alarod pollen phases. Now, those were the two stages that preceded the Younger Dryas, okay? And they were warming phases. So those warming phases were what was associated with meltwater spike 1A. That was then followed by, as it says here, the ensuing Younger Dryas. The temperature fell sharply, the glaciers advanced once more, and the woodlands retreated southward, giving way to open tundra characterized by Dryas octopetala, from which the name of the episode is derived. That's a Dryas octopetala is an 8-petaled flower that likes cold weather. So it flourishes in the cold, it does not do well in the warm, so it disappears, right? So it had disappeared during the Bolling and Alarod warming. It had disappeared. It came back during the Younger Dryas. Here's the term Dryas, which also implies there was an older Dryas, which preceded the Bolling Alarod warming. This phase lasted approximately 1,000 radiocarbon years, from 11,000 to 10,000 years BP. Now, again, this has been updated. 2,000 years roughly has been added to these dates. So you could say 13,000 to 12,000 years. The pollen evidence suggests that the climate turned so cold during the Younger Dryas that it approached the conditions of the full glacial. So what this is showing us is that there was, and there's a lot more, we won't get into that, but this is showing, what I'm trying to show here is that there was this questions being raised about already previous to 2007 about what could have happened. And a bunch of different explanations were being proffered at the time for what could have caused this, what seemed to be the gradual, more natural warming through the Bolling Alarod, its sudden interruption to return to full glacial cold, possibly regrowth of glaciers, and then a second episode of melting, right? Well, the other thing that really seemed to raise questions about this was the fact that it was associated with the Megafaunal extinctions. Now, jumping forward to 3 years, this is Petit in 1995. This was published in the journal Quaternary International. He says the existence of the Younger Dryas cold event has been known for over a century. First named and described from buried leaves and fruits of Dryas octopetala in Scandinavia, the reappearance of these tundra indicators after shrubs and trees had begun to colonize a glaciated landscape during the Alarod warming suggested a reversion to colder conditions. Numerous stratigraphic studies subsequently proved the cooling as characteristic of late glacial pollen diagrams throughout Europe. While the magnitude, timing, and distribution of this event has had considerable attention in Europe itself since that time, it is only in the last 2 decades that the focus has expanded to include the extra-European presence of the signal. In other words, we're reaching a point here now, we're at the mid-90s, 1995, and he's pointing out that within the previous decades, they began to look beyond just Europe. Going, okay, we know that there's this major climate signal in Europe, but what about the rest of the world? All right, so that was where it sort of went. Then he points out that the late glacial paleo, meaning old, paleoecological history of the globe comprises a vast literature. Yes, it does, which would be impossible to summarize in this review. Early reviews of the Younger Dryas European pollen evidence emphasized the dramatic changes in vegetation that characterized both coastal and inland areas. In areas outside Europe, few researchers correlated late glacial fluctuations with the Allarod-Younger Dryas oscillation, but some exceptions exist and are being investigated now with renewed interest. It is the discovery of a clear Younger Dryas signal in the Greenland ice cores in the last decade that sparked additional interest in the late glacial climate. These high-resolution multi-proxy records generated enhanced impetus to understand the cause of the dramatic shift in climate that characterized Greenland and Europe roughly 12,800 to 11,600 calendar years ago. Now, you see here by 95 now they begin adjusting because they now have these high-resolution Greenland ice cores where you can literally count year by year. So as a result of this much greater resolution now, they have revised the chronology. So you can see here roughly 12,800 to 11,600. So 12.8 is lower Younger Dryas, 11.6 is the top of the Younger Dryas. So again, in the question of a global Younger Dryas, one of the major contributions of this working group has been to establish the clear evidence for the Younger Dryas outside of Europe in eastern North America. It is quite evident from the macrofossil evidence that the accelerator mass spectroscopy carbon-14 dating that vegetation responds very quickly to climatic change, both at the onset and the close of the Younger Dryas. The probable extent of the Younger Dryas in the Midwestern USA and along the North Pacific coast is indicated by palynological oscillation at many sites. Palynological is the study of pollen. So whatever kind of plants are growing there, they give off pollen. The pollen can be studied, and you can then reconstruct what kind of plants would have been growing there, right? Were they cold-loving plants, warm-loving plants, something in between? The most convincing evidence outside North America is from Colombia, South America, where many sites show an oscillation, but await clear AMS carbon-14 dating. Through high-resolution sampling and dating in many regions of the globe, we eventually hope to be in a position to state with confidence whether or not the YD was a global event. By focused attention to interpretation of vegetational records, we hope to refine our estimates of temperature or moisture change. Careful analysis of the timing of the YD event in ice core, marine, and terrestrial records will help to expand the pattern of its geographic expression and ultimately may help us understand the mechanism of this dramatic climate change. Okay, so maybe what we should do then is fast forward, but this is okay. Okay, we're backing up a little bit, 2 years, because this is when the ice core results are first in hand, and this is important. This was the atmosphere during the Younger Dryas, published in the journal Science, and Paul Majewski and his team is reporting this. One of the most dramatic climate change events observed in marine and ice core records is the Younger Dryas, a return to near glacial conditions that punctuated the last deglaciation. High-resolution continuous glaciochemical records newly retrieved from central Greenland record the chemical composition of the Arctic atmosphere at this time. This record shows that both the onset and the termination of the Younger Dryas occurred within 10 to 20 years, and that massive, frequent, and short-term, decade or less changes in atmospheric composition occurred throughout this event. The magnitude and complexity, massive, decadal or 10-year scale fluctuations of the soluble species record documented in the YD proportion of the Greenland Ice Sheet Project 2 core provide evidence of an extremely dynamic atmosphere thus far unparalleled in the Holocene, or unparalleled in the last 10,000, 11,000 years. So here now, this is bringing something else into the complexity of the equation, the changes in the chemistry of the atmosphere that are occurring. See, so now this is, and it's showing also that the changes were a lot faster than anybody had been previously thinking. Because it had, previous to this, it had been assumed that we're talking changes that occurred over thousands of years. And that's why this is so significant, is because, as it says here, the record shows now from the Greenland ice sheet coring that the onset and the termination of the Younger Dryas occurred within 10 to 20 years. So now this is really like they're scratching their heads going, what the hell is going on here? You know, scientific literature tends to be non-emotive, so you don't get that. But I can tell you, yes, they were like, what the F is going on? 10 to 20 years, right. And as they say, extremely dynamic atmosphere, thus far unparalleled in the Holocene. So there's been nothing like this. So it happened at the end of the Ice Age, and there's been nothing like that in the last 10 or 11,000 years. It's unparalleled.
Potentially cataclysmic.
Yes, potentially cataclysmic. And you can see where this trend is going. I hope that people are appreciating why I'm trying to give some context to this. What led up to? Now, we haven't even added the question of mass extinction of megafaunal species. But I will jump ahead here to the 2007 paper that came out, published by Richard B. Firestone, Alan West. Let's see, 1, 2, 3, 4, 5 authors. And this was the first indication. We have discovered what appears, this was published at the American Geophysical Union. It was a paper presented at the fall meeting in 2007. We have discovered what appears to be micrometeorites embedded in 7 Alaskan mammoth tusks and a Siberian bison skull. The micrometeorites apparently shattered on impact, leaving 2 to 5 millimeters hemispherical debris patterns, that's supposed to be patterns, surrounded by carbonized rings. Multiple impacts are observed on only one side of the tusks and skull, consistent with the micrometeorites having come from a single direction. The impact sites are strongly magnetic, indicating significant iron content. We analyzed several embedded micrometeorite fragments from both tusks and skull with laser ablation inductively coupled plasma mass spectrometry. Did you get that there, John?
They're using a laser to ablate the surface, and then they're using a scanning electron microscope to look at it.
That's right. You got it.
That's pretty metal while also being pretty nerdy.
Yes, it's pretty metal and it's pretty nerdy. And X-ray fluorescence, which I think what it is they bombard the stuff with neutrons and then they look at the wavelength of the gamma rays coming off. Anyways, these analyses confirm the high iron content in a uniform composition, highly enriched in nickel and depleted in uranium. The iron-nickel and iron-titanium ratios are comparable to Uranite meteorites and are unlike terrestrial sources. So there we go. We've seen the first evidence that this might be something involving an extraterrestrial phenomena. And then let's see down here, the bison skull shows evidence of new bone growth over the micrometeorite impact sites, indicating the animal survived the bombardment. Is dated at approximately 26,000 years before present, which is younger than the tusks. Now, what's interesting here, and as we get into the research, and we won't be covering that today, but we will be most definitely talking about this in upcoming episodes, is the idea that there have been multiple pulses of cosmic impacts, right? And the Younger Dryas was probably the latest and the greatest, but it wasn't a singular, it wasn't the only event, right? So what we're seeing here is evidence that perhaps 26,000 years ago, it appears likely that the impacts, cosmogenic isotope increases, magnetic excursion, and population declines are related events, although their precise nature remains to be determined. Well, after additional evidence and studies, they came out with this paper. and this, as I says here, the paper that started it all in 2007. Evidence for an extraterrestrial impact 12,900 years ago that contributed to the megafaunal extinctions and the Younger Dryas cooling. And you can see, we'll read this together. A carbon-rich black layer dating to 12.9 Ka, that's 1,000 years, has been previously identified at 50 Clovis age sites across North America. And that's the graphic you showed, okay? And appears contemporaneous with the abrupt onset of Younger Dryas cooling. The in situ bones of extinct Pleistocene megafauna, along with Clovis tool assemblages, occur below this black layer, but not within or above it. Causes for the extinctions, Younger Dryas cooling, and termination of Clovis culture have long been controversial. In this paper, we provide evidence for an extraterrestrial or ET impact event at 12.9 Ka, which we hypothesize caused abrupt environmental changes that contributed to Younger Dryas cooling, major ecological reorganization, broad-scale extinctions, and rapid human behavioral shifts at the end of the Clovis period. So we can add to all of the stuff we've already been talking about now megafaunal extinctions and what actually appears to have been the disappearance of the Clovis culture in North America and the abandonment of many of those sites that had been occupied for a number of centuries prior to the Younger Dryas, and then they appear to have been abandoned. So that was in 2007. So that was kind of the paper that started it all. We jump forward to 2008, and then what do we see? Wildfire and abrupt ecosystem disruption on California's northern Channel Islands at the Alarad Younger Dryas boundary, 13.0 to 12.9 Ka. And again, this is what they're seeing from what we talked about before, the evidence, the ammonium and the evidence, the signatures of very large fires. And that was kind of one of the reasons I wanted to go into that, because this evidence of the ammonium and other proxies of wildfires, huge forest fires, preceded this. And now in 2008, in the aftermath, in this new paper, they're documenting the evidence for enormous forest fires, wildfires, and associated ecosystem disruption on the northern Channel Islands. And then again, that same year, the Younger Dryas black mats, Rancho La Brea termination. That was the last phase. Rancho La Brea termination was the last phase of the megafauna occupation of North America. So when they say Rancho La Brea termination, they're meaning that's the end of this last phase of megafaunal presence in the North American biosphere or ecosystem. So in the abstract, and C. Vance Hayes is a very well distinguished, I think he's passed on now. I'm quite sure he is gone because he was even quite old during this when he wrote this. But he was a highly distinguished, highly esteemed paleontologist. So he says that in this paper, of the 97 geoarchaeological sites of this study that bridge the Pleistocene-Holocene transition, approximately 2/3 have a black organic-rich layer or black mat in the form of molic paleosalts. That's just a type of soil. These are all types of soils that he's talking about here. Diatomites, and then algal mats, with radiocarbon ages suggesting they are stratigraphic manifestations of Younger Dryas cooling episode. So he's using the older dates here, then radiocarbon adjusted dates 12,900 to 11,600. This layer or mat covers the Clovis age landscape or surface on which the last remnants of the terminal Pleistocene megafauna are recorded. Stratigraphically and chronologically, the extinction appears to have been catastrophic, seemingly too sudden and extensive for either human predation or climate change to have been the primary cause. This sudden Rancho La Brea termination appears to have coincided with the sudden climatic switch from Alarod to warming to Younger Dryas cooling. Recent evidence for extraterrestrial impact although not yet compelling, needs further testing because a remarkable major perturbation occurred at 10,900 BP that needs to be explained. And then to clarify here, this, you add the 2,000 years to this, and you get the radiocarbon dated adjustments, and that's 12,900. And as he says here, it's a remarkable major perturbation occurred, and it does need to be explained. Most Younger Dryas age black layers or black mats are dark gray to black because of increased organic carbon compared with the strata above and below. Although these layers are not all alike, they all represent relatively moist conditions, unlike immediately before or after their time of deposition as a result of higher water tables. They are both younger and older black layers, but they do not appear to be widely distributed over the continent like the Younger Dryas black mat, nor are they known to be associated with any major climate perturbations, as was the case with the YD cooling. The following observations are based on geological and archaeological investigations conducted over the past 50 years for at least 97 latest Pleistocene sites or localities in North America. And here's a photograph. You see this on George Howard's Cosmic Tusk website. This is the black mat at Murray Springs Clovis site. We visited this, myself, Brad Young, the Serpent Brothers, Russ and Kyle. Who else was with us? Yeah, we visited this site. This is actually not the thickest example at the site. There's places where this looks to be 8 inches to 10 inches thick. But you can very clearly see it. And so this is that lower Younger Dryas boundary right here. Below, you find evidence of megafauna, you find evidence of Clovis. Above, you do not. Now, there are some exceptions, yes, because there were some limited survivals across the Younger Dryas boundary, or so it would appear. But it also is evident that a major mass mortality event did occur right here associated with this boundary. Okay, so this was a photograph from a paper that was published in 2011. Evidence for Younger Dryas global climate oscillation and human response in the American Southwest. So look at this. I mean, look at how prominent this black mat layer is. A late Pleistocene coral marl scoured by alluvium underneath a thick YDC black mat in a tributary stream of the upper San Pedro Valley, southeastern Arizona. Now, I have not been to this site, but I definitely would like to get to this. But you can see how prominent it is here. It says the post-Clovis. Listen again, the Clovis, and we have to talk about the Clovis culture in more depth because they raise some interesting questions themselves. The post-Clovis archaeological record of the Southwest has been explained by the early development of a desert archaic adaptation, okay? The most significant post-YDC, that's Younger Dryas chronozone, change in material culture is the appearance of groundstone and pinto type and notch projectile points. So after the Younger Dryas, there was a change in the type of tool and artifacts that they found. But here's the key right here. In southeastern Arizona, a noticeable 1,400-year hiatus occurs in the archaeological record following Clovis and Pleistocene extinction. So in other words, you've got the black mat layer, the megafauna disappears, the Clovis culture disappears, and then for 1,400 years, there's no evidence of human occupation. That's what it's saying here. And then you have this new type of artifacts that show up, what they're calling the pinto type notch projectile points that occur between 9 and 8,000 years before present. In any case, there's no compelling evidence for hunters or gatherers in the northwestern Chihuahuan Desert or the Sonoran Desert interior during the Younger Dryas chronozone. So, in other words, it's evidence that the fairly prolific Clovis culture disappeared from both the Chihuahuan Desert and the Sonoran Desert. Now, in the old models, well, they must have gotten up and left and gone somewhere else. However, the problem is when you start looking at the somewhere else sites, you see the same thing happening. So it's far more looking like, rather than migrating outside to another location, they didn't actually migrate, they disappeared. They became extinct in that area. Yeah, to isolate a human response to Younger Dryas chronozone climate changes requires controls that are not always possible using the types of evidence at hand. But our analysis does demonstrate unambiguous and large-scale changes in human land use. Then the apparent, down here, the apparent abandonment of the northwestern Chihuahua and Sonoran deserts by hunter-gatherer populations after 12.8 thousand year, means calibrated years before present. And the reappearance of people in the stratigraphic record of the northwestern Chihuahua and Sonoran deserts around 10,000 Ka or 11.5. So in other words, what you have here is you had evidence of human population, and then they appear to have disappeared. It's abandoned. The sites where they were occupying, hunting and gathering, making their tools, making their spear points, all of this, they're gone. And then there's a hiatus, and then after about 1,500 years or even longer, you see the evidence of cultural occupancy once again, and their artifacts are different. It's like, a good archaeologist who's studied these can look at the two and quickly see the difference between the Clovis artifacts and those which followed. So Albert Goodyear, we got the tour of the Savannah River site, which was a Clovis site by the lead archaeologist, Albert Goodyear. And what was interesting, the story he told us, he said that for years, that he'd been studying it. He had this Clovis horizon that he'd been studying, and if I recall, in an upcoming future episode, I can show you photographs of the site. But maybe 6 feet down below the surface, something like that, 6 or 7 feet, there was this Clovis horizon that he'd been studying. And he said, that various people had come there. Sometimes he brought tours in. On several occasions, they brought, I think, even like college students or even high school students out to look at the site. It was on private property, so you could only get in there with permission from Al. But anyways, he said that they kept asking him, well, what's below it? What's below the Clovis site, the Clovis layer or Clovis horizon? And he said, well, we haven't really looked. We don't assume there's anything there because the dominant paradigm was Clovis first. And they were the first people to come to North America, and they probably came across the Bering Land Bridge connecting Siberia to Alaska, migrated down through the ice-free corridor between the Cordilleran and Laurentide ice sheets right there just east of the Rocky Mountain front in Alberta. And this was the explanation, and it was all pretty much resolved. Everybody agreed that was the case. Clovis were the first. And so he never really looked below. Well, he said finally he got asked enough by enough people, probably, ignorant high schoolers, who would ask questions like that because they didn't know what the consensus opinion was or what the dogma was. So he says, well, he finally decided to take a look. So he did, and he looked down below and discovered more evidence of occupancy of the site that goes back almost 50,000 years, if I recall the number, which I thought was very interesting. But then, of course, there was a hiatus, and then you have this mysterious Clovis culture that shows up around 13,400 years ago. And they're there for 300 to 400 years, and then as quickly and as mysteriously as they show up, they disappear. To the paper co-authored by Goodyear, James Kennett, Alan West, and David G. Anderson. So check this out now. Okay, this is in the journal Quaternary International, which is one of my favorite journals to read every month. The Paleo-Indian Database of the Americas integrates database and geographic information systems technology to provide location data for almost 30,000 Paleo-Indian projectile points, measurement, and other qualitative attribute data on more than 15,000 points, and provides photographs and or line drawings for nearly 10,000 Paleo-Indian points across North America. Now you can go to that Paleo-Indian database of America. It's really interesting to go there and spend some time perusing that site if anybody wants to check it out. So these data clearly indicate, this is where it gets interesting here, these data clearly indicate a major decrease in the number of artifacts in many parts of North America during the early centuries of the Younger Dryas. This decrease is interpreted to represent a decline in human populations and or a major reorganization of settlement systems, something likely related to the major changes in biota observed over this same general interval. In the southeastern U.S., this decline is particularly dramatic, amounting to a drop of approximately 50%. The pattern of immediate post-Clovis decline in eastern North America is also similar in the central part of the continent, in an area defined by 21 states and provinces in the Great Basin, Rocky Mountains, and Great Plains. We'll just go looking at the underlined portion here from the same paper. Nevertheless, a wide range of evidence indicate that conditions during the initial few centuries of the Younger Dryas caused a significant drop in human populations or dramatic reorganizations of settlement in North America, and possibly also broadly throughout the Northern Hemisphere. Well, we're not going to get into it too much in this episode, but we are going to look, because there's a lot of data now from around the world of how this affected human populations. So on the next one here, the next graphic, you'll see here the distribution. You see there's a very thick clustering of points in the east particularly, and more sporadic, but there's a lot of, these are places now where Clovis artifacts and Clovis spear points and so on have been found, right? So quite a thick clustering over here around the east United States, down into Florida, over here, down here in the southern desert regions here, up on the Colorado Plateau, all the way up here into the unglaciated part of southern Canada. You see portions of the Cordilleran ice sheet over here, over the Rocky Mountains, portions of the Laurentide ice sheet here. Now, look what happens after 13,000 years. Particularly look along the East Coast, along the eastern. Boom, they're gone. And they're not nearly as thickly clustered. This is Folsom. So this is 12,000 years. Let's go back. This is 13,000. So this is the beginning of the Younger, just at the eve of the Younger Dryas. This is what you've got. The Clovis culture is widely distributed over unglaciated North America, thickly inhabited apparently in some regions, particularly the east, and then 1,000 years later, they're gone. And you've got, in fact, the points that are now showing up are of a different cultural group altogether called the Folsom. And to a trained archaeologist, you can look at a Folsom point and a Clovis point, and they're distinctly different. You can tell the difference. This next graph is interesting. Now, this is the Topper, South Carolina site. That's the site that we visited with Al Goodyear at the Savannah River. Well, these are two more Clovis sites, Adams, Kentucky, and Carson, Con, Short, Tennessee. Now, if you look over here, total number of artifacts are on this vertical axis here. So you can see at the Topper site, over 400, 450 roughly artifacts were found, during this period of Clovis occupancy. The Tennessee site was up to over 800 artifacts. The Adams, Kentucky site, almost 1,000, right? Then look, here's the Younger Dryas boundary right here, and here's post-Clovis. So boom, what's happened? These people have disappeared. Now the question is, where did they go? Well, did they pull up their stakes and move somewhere else? Well, no, because the abandonment of these sites was pretty much continental. They didn't go anywhere. They died out. They disappeared along with the megafauna. So you can see here how this whole episode is getting extremely and compellingly interesting. We can see on this next graph some various, so relative probability. You can see here 80% here, 80%, 100% here. So this is, what this is showing is that this is where the disappearance is occurring, right in here. We'll skip this and come back to it because I have more detailed information on explaining these graphs, what they're actually showing. We won't get into that here today. Yeah, the late place. So this is from a different paper, also published in 2011, the Younger Dryas and Late Pleistocene Peoples of the Great Lakes region. The late Pleistocene archaeological record of the Great Lakes drainage area shows that there were several, albeit spatially variable, changes in that record in a time period corresponding to the Younger Dryas climate reversal. Notable here are declines in some areas in the mobility of Paleo-Indian groups as measured by distance to the main lithic source employed. Declines in the overall frequency of sites and find pots, particularly in the western Great Lakes, where some northern areas seem to have been largely abandoned. And an increasing association of occupation locales with glacial lake shores or extensive wetlands left by recently drained glacial lakes. Some of the changes, as in range mobility, most likely relate to the colonization of new areas rather than directly to the Younger Dryas. Specifically, the earliest groups were able to target rich but widely dispersed resource locales due to an absence of competing groups. Now, why I have that underlined is because this is talking about in that post-Ice Age world. So what's happened is that the earlier areas were largely abandoned, and then after this hiatus, you have a colonization of these new areas after the Younger Dryas. And as it says here, these earliest groups in this recolonization were able to target rich but widely dispersed resource locales due to the absence of competing groups. In other words, there were these groups that came into these areas and there was nobody else there. Basically, that's what it's saying. And so they were target-rich resource locales because in the aftermath of the deglaciation, you had this period called the climatic optimum. So during the climatic optimum, the climate got quite warm, warmer than now. You had this proliferation of plant life, of vegetation. You had the proliferation of small game. You had large areas with no human occupation. Now you have these small groups going into these resource-rich areas. There's no competing groups there. So this is, I think, an important model that's emerging from this whole scenario that we're describing. Now, how long does it take before those small isolated groups then grow large enough during the climatic optimum that they finally eventually bump up against neighboring groups? Well, the answer is probably at least 3,000 to 4,000 years, right? So, anyways, let's look at some of the evidence in these two new papers. We're going to come back, but I think what we should do is, because it's topical and timely, we'll look at these two papers briefly and what they have to show us. There's a whole bunch of research, very interesting research, particularly when you look at the controversy and the debate that went on between the celestials and the terrestrials, to borrow phrase from the early controversies over the Carolina Bays. There were two groups, the celestials, who believed the Carolina Bays were the result of some type of a cosmic impact event, and the terrestrials, who believed that it was a clustering of terrestrial events. In fact, Douglas C. Johnson, who was one of the dean of geomorphology at, where was he, at Columbia University? I think it was Columbia. He wrote an extensive paper intending to debunk this outrageous idea that there may have been an impact that created the Carolina Bays. And it was called The Origin of the Carolina Bays. And his theory was called the complex theory. Well, if you recall Occam's razor, it's like always try to look for the simplest explanation first before you go into the more involved explanations. Well, the clue was the title of his theory, the complex theory. And that was short for Artesian solution lacustrine aeolian hypothesis. Artesian solution lacustrine aeolian hypothesis. So artesian, look up artesian aquifer. So that's where it starts, with the idea of an artesian aquifer.
The word artesian comes from the town in Artois in France, the old Roman city of Artesium, where the best flowing artesian wells were drilled in the Middle Ages to the level which water will rise in tightly cased wells in artesian aquifers called the potentiometric surface. Potentiometric surface, there you go. That's via the USGS, so water under pressure.
Okay, so picture this. Layers of bedrock and water flowing down gradient in between what's called a perched water table. Water flowing, it's under pressure. Now it gets to an aperture in the bedrock, right? So because it's under pressure, it gets to this point within this layer, this conduit, where there's no overlying lid or ceiling holding, that's creating the pressure. So it gets to that overlying aperture, and what does it do? It immediately goes up. And as it goes up, you've got limestone, it's dissolving the limestone. It's solution. So you go from artesian to solution. And now artesian solution, lacustrine means lakes. So the water emerges from the ground and forms a lake. And then aeolian means the wind. So the wind is now blowing on the water, and the waves somehow, mysteriously, in a rather undefined way, circulate, and they shape those irregular bodies of water, the lakes, into these nice, perfect elliptical shapes. And that was Douglas Johnson's theory, a complex theory, artesian solution, lacustrine aeolian. And that was how he explained. So essentially he brought in all of these geomorphic processes related to flowing water and wind and dissolving bedrock to try to explain the Carolina Bays. And I was very suspicious when I read his book, probably 30 years ago. I think he wrote it in the 1950s. And I was able to get through interlibrary loan, I was able to get an original copy, which I then photocopied. So I have a photocopy of his book, which I'm sure is long out of print, in which he's trying to dispel, to debunk this outrageous idea that it could have been somehow extraterrestrial. Now, what's the explanation for the Carolina Bays? I lean towards extraterrestrial, but quite frankly, I don't know. Now, there's going to be some presentations again at the Cosmic Summit. Chris Cottrell has emerged as one of the leading authorities. He's really studied into all aspects of the Carolina Bays. What's his name? Tony Zamora has come up with a theory, which is quite interesting. I know others, scientists, that dispute his theory, which is basically there was a major impact into the ice sheet, the southern ice sheet. near the Michigan Basin, and this caused a rapid injection into the ice, into the atmosphere of hundreds of thousands of chunks of ice that then rained down over the eastern United States and on the coastal plains of the Southeast, where you find the Carolina Bays, and you might pull up Carolina Bays and we can show some people what we're talking about. I bet a lot of the listeners are already familiar with Carolina Bays, but his idea was these large chunks of ice landed on the landscape, which was composed primarily of unconsolidated coastal sediments, and the meltwater, the sheets of meltwater flowing towards the ocean, because the coastal plain, of course, is tilted towards the ocean. That water scoured out the elliptical basins. Oh, okay, there we go. There we go. There's some Carolina Bays. These natural depressions pepper the landscape of the Atlantic coastal plain. Around 36 of these features can be found in this image, but there's thousands of them. We, on that same trip that we went to visit the Topper site with Al Goodyear, please forgive me. With Al Goodyear, my apologies, Al, we went with Chris Moore, who is one of the leading scientists working and members of the Younger Dryas Impact Group, the Comet Research Group. But we went out with him to some of the Carolina Bays. He believes they're more or less terrestrial. And I don't want to attempt to explain his theory of origin because I wouldn't do it justice, because I haven't taken a detailed analysis of it. So we'll leave that for now. But yeah, if you there's probably a lot more images to give people sort of an overview of what the Carolina Bays are. And when I first started learning about the Carolina Bays in the 1980s, it looked like they were terminal Pleistocene. And this was based on core studies taken from the bottom of a number of Carolina Bays, radiocarbon dating sediments that were enclosed within radiocarbon dating organic material that was enclosed within the sediments at the bottom of the Carolina Bays. And they kept coming up, they looked like Younger Dryas. I mean, they looked terminal Pleistocene. What's going to be the final answer on that? I don't know. Again, we would need probably a lot of new studies. Okay, so we'll just show this mosaic here. This was some of the first aerial surveys ever done, 1930. And you can see all of these are individual photographs that were taken from the air and then pieced together. And surprise, surprise, it showed all of these elliptical features. And this is just a small little area of it, and there's thousands of them. And we could get into an episode on the Carolina Bays. I think it would be interesting. I won't claim to have the most recent ideas on them because I did study. I mean, most of the research I did on the Carolina Bays was in the late 80s and early 90s. In fact, I think it was 92. I went down to South Georgia where some of the Georgia bays are, and I went to a local airport and I hired a pilot to take me up and fly me over because I wanted to see them from the air because you can't, they're hard to see from the ground. So I have some of those pictures that we can share in the future, but this is right here. You can see some of the perfect ovals and how the long axis of the ovals are parallel. And so what this led to was the idea that if these were impact produced or somehow, or maybe also produced along the lines of the Louisiana, and this is a good segue into this recent paper on the Louisiana feature that we're about to talk about, but because it's very possible that, and this is, in my opinion, I talked about Tony Zamora's idea that there was a what does he call it? But imagine large chunks of broken ice landing on the coastal plain. And also I want you to notice, like, take this one, it's very noticeable that there is a very prominent sand rim on the south and southeast sides here. You see that? And less on the north. Well, this would be consistent with an oblique impact from the northeast, right? Which would blow the sand towards the south. I mean, in other words, if this was impact produced, the idea was that it was a very low angle to the horizon. Otherwise, it would have been circular. Because if you take a cone, and we're going to see evidence that this is what it looks like we're seeing on this Louisiana feature, is that there would have been a plasma cone preceding the arrival of the object, right? Well, if you take a cross section of a cone at an angle, you get an ellipse. Okay, so if like you had a plasma cone intersecting the surface of the land, and that is a high pressure feature, and it's blowing out, because remember, the substrate here is more or less unconsolidated. It's not hard bedrock, it's coastal plain, so it's a relatively soft ground, right? So that's what I initially believed, that it was probably going to be something along the lines of a Tunguska event, that there may have been a pressure cone preceding it, that the thing didn't actually hit the ground, that it exploded in the atmosphere, something along the lines of Tunguska or this new study of the Louisiana event, and then created a cone of pressure, and that cone of pressure intersects the horizontal surface of the land, and hence that's where you get that cross-section slice of the cone, and it gives you an ellipse, if that makes sense. Note parallelism of long axes of ellipse and prominent sand rims on the southern and eastern sides. And then the next slide shows the long axis and the parallelism. Now, that to me was always one of the sticking points with the terrestrial hypotheses. How do you explain that? First of all, the perfect ellipses. Second of all, the parallelism of the long axes of the ellipse. But it seems to me that some kind of a terrestrial event superimposed from above is going to be more easily able to explain these features. One, the elliptical shape, the prominent southeast sand rims, the parallelism of the long axes, the shallowness of the crater material, of the crater form itself, which in most cases has then been infilled with Holocene sediment. Okay, so here's the new paper. Let's see. This just came out. It was published online the 4th of June. Okay, so this is really only barely more than a week and a half old since this paper was published. And it's entitled Evidence of a 12,800-year-old shallow airburst depression in Louisiana with large deposits of shocked quartz and melted materials. And that's just, see, the shallow airburst depression, that was the original concept I had for Carolina Bays, is that they were shallow airburst depressions. This expands on it quite a bit. I have to confess I have not studied the paper yet. I've scanned it and to just get the highlights, but I have not studied it in depth because I only fell into my hands 2 days ago and I've not been able to really take a deep dive into it yet. But it says here, we report evidence of a likely low-altitude cosmic airburst near Perkins, Louisiana, associated with semi-consolidated deposits containing abundant shocked quartz grains, which of course is an important proxy, a classical impact indicator, along with spherules, meltglass, microbreccia. Now, microbreccia is microscopic material that is basically during the heat of the explosion and the violence of the explosion, the rock, the bedrock is broken up into billions and billions of very small microscopic pieces, and that's what you call the microbreccia, the broken rock. Breccia's broken rock. And then you've got a bunch of really sophisticated analytical techniques that they used. In fact, they used 8 different analytical techniques. I think we will not get into all of that right now. It's very interesting, and people interested in this should have just a basic working knowledge of some of the techniques that are used. Scanning electron microscopy is probably one of the main ones. Optical microscopy, which is just simply an optical microscope. Cathodoluminescence, laser ablation, we came across that one. Neutron activation, radiometric dating, that would be like radiocarbon dating. So these analyses revealed that the deposits exhibit morphological and compositional similarities to known impact-related proxies. Radiocarbon dating, based on the isotopes of argon 40 and 39, analysis constrained the likely age of deposition between 30,000 and 10,000 calibrated years before present, but there's a concentration of dates clustering around 12,800 years before present, coinciding with the age range of the Younger Dryas boundary. Spheral and meltglass abundances, along with evidence of high temperature mineral transformations, are consistent with the effects of a high energy airburst or impact. Hydrocode modeling suggests that a touchdown airburst could plausibly account for the observed shallow depression, material dispersal patterns, and geochemical signatures. Now we're looking at the this new paper, and this is the paper is entitled Evidence of a 12,800-Year-Old Shallow Airburst Depression in Louisiana with Large Deposits of Shock Quartz and Melted Materials. So here we go, and this is showing the area in Louisiana right here in the box. And then this is a closer up. There's a lake. Notice there's a lake right there in the center of this circle of dots right here. And this is the town of Perkins, Louisiana. Let's go through and look at this. Here we go. So here's is this a Google map or Google Earth? So here's Lake Depression, seasonal lake, with locations of glass and spheral rich material outlined in the white dotted line. The pond deposit, which is right up here, is northwest of the Lake Depression. Let me close this down a little so we can see the whole thing. Okay, so they dug a trench right here, another deposit down here. The pond deposit is northwest of the Lake Depression, and the V deposit is south of the Lake Depression. Trench number 1 is on the east rim, so they trenched right here. And the lake deposit is within the Lake Depression. Calibrated radiocarbon ages on organic material and carbon-rich meltglass are shown for 3 key deposits. Okay, images, yeah, your Google Earth. So then they get into information on airbursts. Cosmic airbursts can occur at various altitudes, producing distinctly different surface effects. High-altitude airbursts, like the 1908 Tunguska event, primarily cause widespread devastation through blast waves, but typically leave no craters. Now that's really, I think that's important to keep that in mind. Even so, the airburst evidence at Tunguska has been reported to include spherules, shocked quartz, glass-filled fractured quartz, melted feldspar, carbon spherules, and glass-like carbon. Shock quartz, I will mention, is any kind you have quartz crystals and shocked because they have fractures all throughout. And I think we've got pictures here of some shocked quartz. Let's just look at some of the, first of all, the macro scale stuff. So it says here, this is optical photographs, which is just your typical microscope photographs. But this last one is, I find, very interesting because here you see the spherules that are embedded in this matrix. Like here's melt glass from within the matrix, and look at what you have here is vesicles, which were formed by gas bubbles. So this is some of the rocks that were picked up, some of the matrix material. If you look at this, let me zoom in a little here. You can see that there's this material, darker colored material spread throughout here. Here you've got glass, this dark colored glass embedded within this matrix. And yeah, here you can see the vesicles. And then here you can see spherules.
Would we call these proxies?
Yes, these are proxies.
Those don't happen naturally in the rock. It has to be pretty hot, doesn't it?
Yes. So yeah, here you have, this was formed by meltglass, right? This is meltglass. So here this lighter is sort of the matrix, and you've got the meltglass, and then you've got the spherules. So the original discovery was of a sizable semi-consolidated surface deposit, primarily comprised of billions of spherules and fragments of meltglass embedded in a matrix of partially melted and unmelted grains of quartz, sand, and limestone. So here's, F is your photo micrograph of spherules embedded in the pond deposit matrix. Let's see here.
So you'll see a graph on page 10 of where they believe the air burst.
Okay.
Oh, there's your arrowheads.
Yeah.
Your pre and post Clovis and boundary.
Yeah, here we go. Yeah, so interesting. There's your accelerator mass spectrometry, 12,000. Yeah, so here's your Younger Dryas boundary date right here. And here's the peak, the glass peak right here from 12,835 to 12,735 calibrated years before present. Let's see, you said 10.
Page 10, you got a good layout of where they think the air burst occurred. You've got your cone imprint on the landscape.
I must be close to 10 here.
That's it.
Oh. This one?
This is the one.
Spheral distribution.
So this is where they took all their core samples.
Uh-huh, yep. So each one of these numbers, I presume, is a core sample.
Mm-hmm.
Mm-hmm. Okay.
And this is where they found all of our proxy spherules.
And it's actually quite a collection of diverse proxies in one place.
Yeah.
Which, to me, is very much indicative of an impact. And the dating would certainly suggest that it was right there near the Younger Dryas boundary. Meltglass. So let's see, there's some of the temperatures we're talking about for meltglass are really impressive.
Oh, yeah.
Let's see, so this is kind of an oblique view, a profile across the lake depression showing spheral peak by depth. Okay, so right here by the lake, notice that the spherules are much deeper. Well, that would seem to suggest to me that this is probably right where most of the energy was concentrated and was able to excavate a deeper, and that's what's now occupied by the lake. Let's see what else we've got here. Oh, yeah. Oh, wow, look at this. Spherules from various deposits from several locations. So A through C are photomicrographs. And look, you see the spherules embedded there.
These are from just south of the lake, southeast, on the V deposit.
Yes. And then D, E, and F are, let's see, scanning electron microscope image with two epi-illuminated photomicrographs of the thin-sectioned spheral-rich matrix. Panels D and E exhibit approximately 800 spherules, representing approximately 1.8 million spherules per square centimeter. So that's just a little, that's a lot of spherules in a very little space. But look at this stuff. Pond deposits. Let's see what it says about those. So that's G. Images of spherules within the matrix. In panel G, number 7, is an iron-rich spherule right here. with a platy texture. Look, see the platy texture it's talking about, which would be suggestive of, violent pressures imposed upon these spherules. In panel H, number 8 is a hollow aluminum silicon-rich spherule surrounded by hundreds of smaller spherules. You see here, like all of these smaller spherules. In panel I, 9 marks a small hollow spherule, a few microns in diameter, and number 10 marks an elongated iron-rich object. So it looks to me like there's a bunch of stuff that's kind of all become fused together here, which is typical.
It looks like what you see after you get done welding something or smithing something. If you ever actually work with a hot iron in a forge, looks like everything that's in the bottom of the floor of the shop. Hot and violent.
Okay, so these are all from the V deposit, which is just south of the lake. Platy textures characteristic of iron-rich spherules, covering an aluminum silicon-rich core at number 2. So that right there. So this is what he's calling the platy texture. I mean, look at this one. So what does it say about B? Platy textures and number 4, dendritic textures on iron-rich spherules surrounded by a spheral-rich matrix. So this is basically all broken up. Now let's see, pit D, spheral D was from pit 3. Let's see, number 5, impact pit on a spheral. Right here, right there. So you had a spheral and you had a smaller piece that slammed into it right here and created that hollow, that indentation right there. Look at E and F. Okay, so E and F, splashes of once molten material draped across an aluminum, calcium, silicon spherule. Number 8 is a cluster of submicron spherules splashed onto the large spherule. Oh yeah, look at this. Here you see the large spherule, and then you see that these have been basically welded onto it. Look at G. G says it's a iron-rich spherule that collided with number 12, an aluminum silicon-rich spherule. So there, yes, 2 spherules that collided and then stuck together.
And all of these are found where?
Well, these are all part of the V, which is that site, just all of them except for D, which was pit 3. All of these are found in the V deposit just south of the lake.
Well, I meant geologically. They're all in the...
Oh, well, they all appear to be clustering around the Younger Dryas boundary.
So... At least this event, at least this black mat was exposed to something very, very hot, very, very fast. We have what looks like an airburst impact. Yep. It's hard for me to imagine anything terrestrial that would create this naturally other than a volcanic activity.
Well, no, even that wouldn't, because the pressures in volcanism and the heat necessary to create these spherules is insufficient.
And it's the wrong material.
Mm-hmm.
And it's the wrong material. It wouldn't be coming fast enough. Yeah, I'm with you. There's nothing terrestrial.
Right. Look at these spherules. Wow, what a collection of spherules these are. And it says they're extracted from the V deposit. A through D is clusters of iron and aluminum silicon-rich spherules. Multiple colors of glassy. We have calcium, aluminum, silicon, iron, carbon-rich spherules. L, JKL, a hollow, broken, glassy spherule containing numerous submicron spherules inside of it. Yeah, look at this one. So here's a hollow, broken, dark-colored, glassy calcium, aluminum, silicon, iron, carbon-rich spheral. Miller-Bravais indices confirm shocked quartz. Geez, what a collection of stuff from this one site. Multi-layered V-spherules. Multi-layered spherules. Yeah, I'm going to have a good time working my way through this.
Yeah, it's quite the read. It's 47 pages long. So if you guys want to have a look at that, link will be in the description.
Yeah.
To this article and the Russian one, which is nowhere near as replete as the one from Louisiana. We're going through the most interesting of the two. But the fact that there's one in Russia now, and we have proxies, impact proxies in the Younger Dryas boundary layer.
Yeah.
What would that intimate, Randall?
Ooh, well, it would certainly, to me, suggest that. I mean, it seems that what it amounts to is we're drawing boundaries around the extent of the Younger Dryas boundary event, but it seems to be constrained only by as far as we've actually looked. And when we look at new places, it keeps showing up. I mean, it to me, it points in the direction that it was global in extent, and that's what I think we can conclude from this. And when we go through, we'll take on another episode of this where we sort of like try to fill in the gaps. We'll address some of the criticisms of the theory, and look at some of the popular in the popular press, some of the way they treated it. And it was always kind of over glamorized, over sensationalized, and then 6 months later they would have the headlines would be impact hypothesis disproved, right? So there was a lot of controversy, but I think the controversy has kind of subsided because the evidence favoring an event like this keeps accumulating. I think what I'd like to do is zoom to the, let's see, I was looking for the graphic on the plasma plume.
I believe that's on page 37.
Ah, there it is. Okay, yeah. Melted and shocked quartz during an airburst. So this is what they call a hydrocode model of an asteroid airburst showing crater formation. Look at this. Okay. And here you see down here crater formation. You've got this high energy plasma plume that hits the surface of the ground. This model by Boslow and Crawford shows the jet from an asteroid airburst excavating a crater, melting superficial material at greater than 5,500 degrees Kelvin.
Yeesh.
Which is yellow. That would hurt if you got burned up. If you got swallowed up by a 5,500 degree Kelvin plume, which is yellow, as it says, and ejected a bladed material, which is the small black dots. So you see, let's try to zoom in a little more. Okay, so there you've got all of this is the ejecta that's being blown out of the crater. And then that falls, some of it falls to the outside, some of it falls back within the crater itself. Melted materials such as those produced under these conditions have been observed at Perkins. So this is most likely the event. It didn't actually, the object itself didn't strike the Earth. Okay, visible representation. So you got a low density, low velocity impactor coming in like this. Then what's happening here? So this would be the ejecta plume going out this way. Let's see, visible hydrochroma, possible low density to low velocity impactor. The legend shows various materials after a 350 meter comet broke up in an airburst, 108 kilometers high. One 100 meter wide ultra low density fragment, shown in red here, struck the Earth traveling at 0.975 kilometers per second at an angle of 45 degrees. Earth's surface was relatively flat with vegetation and trees. And then at 765 meters, the impacting airburst fragment created a shallow crater approximately 25 meters deep. You can see that that's right here. It's forming this crater, shallow crater right here. Because the airburst fragment was much less dense than the Earth, it broke into a laterally moving cloud of small particles shown in red. That's what this is. What I was saying is the ejecta, and it moved all the way over, and then it kind of did this wave coming back on itself here. It broke into a laterally moving cloud of small particles. The impact created pockets of near vacuum conditions in white and began to vaporize vegetation at number 3. After 2,235 meters, the crater deepened. Oh no, this is probably milliseconds, not meters. Sorry. Apologize, everybody. This would be milliseconds. The crater deepened, and the denser vegetation deflected the low-density impactor cloud. So there we go. That's kind of a cross-section of what would have created this. A low-angle impactor, low density. If it's a piece of a comet, it's going to be low density. Low density, low velocity impactor. And what's going on here? A 100 meter wide ultra low density fragment of a 350 meter comet struck the Earth, as described in the figure above. After 720 milliseconds, the impacting fragment created a shallow crater. Temperatures rose to more than 2,000 degrees centigrade in red, the boiling point of quartz. At 720 milliseconds, the comet fragment broke into a laterally moving cloud of small particles. The high temperatures began to vaporize vegetation. After 2,235 milliseconds, the crater deepened, and greater than 2,000 degrees centigrade temperatures continued to melt superficial sediments and vaporize vegetation. So here you can kind of see. So here's the path of the incoming object. This would be the plasma plume intersecting the ground here. And here you can see all of this would be ejecta thrown out from the impact site. And in fact, you can see there's an outer layer, an outer boundary to the ejecta here. And it looks like ejecta thrown out this way as well, almost in a butterfly type shape. Not unlike the distribution of tree destruction with the Tunguska object. So we used a LiDAR-derived digital elevation model to show a potential crater with an ejecta apron to the west, with 2 possible wings of debris extending away from the crater lake. An additional potential crater is shown in blue. That's right here. And that would certainly fit and be possible, which warrants investigation. Elevation in black. The vertical scale is meters above sea level and is exaggerated several times for better visibility. And then you have your conclusions. Go through that. Let's see here. So in the conclusion, We propose that the Perkins Lake/depression represents an airburst impact crater associated with the Younger Dryas onset, and as such contributes to the broader understanding of the frequency and effects of cosmic impact events on Earth's surface environments. Recent research, extensive research, and observations at this site and elsewhere imply that airbursts, now this is important, I think this is the one takeaway of this that people should really take with them. Airbursts have been more common than currently accepted, and that numerous easily overlooked such airburst impact events may have occurred in the past. Well, why would they be more common? Well, it's because they don't hit the ground and gouge out large craters that can be studied, years later. And that's something important to keep in mind. Why? Because if they are more common, here's the thing. If we look at a crater like Meteor Crater in Arizona, it was an iron asteroid. Okay, an iron asteroid is a very dense object. And because of its density, it's able to penetrate much more readily through the atmosphere, strike the ground, and gouge out a big hole, right? Whereas a low-density object is only going to create a shallow crater, whether it's Tunguska, whether it's this Perkins crater in Louisiana, or possibly the Carolina Bays, right? Now, here's the thing about the Tunguska. Another century or two, you would scarcely see any evidence that this event had even happened there. Whereas, when it was first reached by scientists back in the late 1920s, the blowdown of the trees was still extremely apparent, right? So a lot of information has been able to be derived by looking at the pattern of tree destruction and, looking at the site for proxies. But, if you're just walking through the woods, like, a century or two from now, you'll be going, there'll be pretty much full recovery. Who's going to think let's excavate a sample of Earth and see if there's microspherules or nanodiamonds or shock quartz or any of that stuff in it? No, you wouldn't even think of that, right? So here's the thing. The iron asteroids that leave craters, like when you go in, there's approximately 200 impact craters now identified on the Earth. Well, the vast majority of those are going to have been created by higher density objects like asteroids, right? In the event of an airburst, a la Tunguska or this event here, it is not going to leave an obvious crater whose signature is so obvious that you're immediately going to go look at it and look for all the impact proxies that would normally be associated with an impact crater. But the iron objects, compared to the low-density objects that would cause airbursts, those low-density objects are about 10 times more abundant than the iron objects that gouge craters. So what does that imply? It implies it could have a lot more airbursts that we don't even know about, and that's the point. That's the point that they're making here in this article, is that yeah, it's very possible that these things are a whole lot more, that they're easily overlooked, and that numerous easily overlooked airburst impact events may have occurred in the past. But, 1,000 years later, 500 years later, how do we identify those? Well, maybe this is where LIDAR will come in. Maybe things will show up, because certainly the Carolina Bays are showing up quite impressively in LIDAR mapping. So one more thing here. Hydrocode modeling supports the hypothesis that a low-altitude airburst impact could have generated the observed depression and associated deposits. While alternative explanations for this material, including natural, fluvial, or anthropogenic processes, were considered, they failed to account for the full suite of geological and geochemical evidence.
So, Randall, what's the ultimate takeaway here? Airbursts happen?
Airbursts
happen.
Yeah, airbursts happen. And in our estimates of how numerous cosmic encounters are, I would suggest are being grossly underestimated. only because they're primarily derived from crater counts. And as I just explained, those crater counts are based upon actual impacts into the surface of the Earth. And an event like Tunguska, or this event here, we'll call it the Perkins, Louisiana event. Yes, now we can come back, thousands of years later, because there is a depression there. And that depression, it appears, was formed by a high pressure, high temperature plasma plume that was preceding the encroaching object, right? But if we go to the Tunguska object, and I think there are actually shallow elliptical craters in the region of Tunguska, which would suggest to me a higher likelihood of that being an explanation for the Carolina Bays. But in any case, if you have a Tunguska object, my point being that if you have a Tunguska object that happened 1,000 years ago, what's going to be our evidence that we can look for in the field? Well, if you have fossilized trees from a blowdown, that could do it. But typically you get back several millennia, they're going to be buried. You're not going to see them still laying on the surface, because if they are still laying on the surface, they're going to likely have decayed away and become just part of the soil, and you wouldn't even know they were there. So the takeaway is that the real danger, the most immediate danger, would be airburst phenomena rather than impacts. Impacts are still highly dangerous. If say an object 1,000 feet in diameter slammed into the Earth, we're looking at global repercussions of that, or reverberations. I mispronounced reverberation in one of our previous, I called it reverbation when it should have been reverberation, but hey, what can I say? I get tired, and sometimes I occasionally mispronounce a word. Supposedly, anyway.
I was going to say supposedly, yes.
I supposedly mispronounce words from time to time, but that's the takeaway here. Tunguska-type events may be far more numerous than we had previously estimated. And here's the thing, a Tunguska event is extremely catastrophic and devastating and damaging to the immediate local area, right? But a single object is not going to really have global consequences, although the Tunguska event did have some global fingerprints that we can talk about in an upcoming episode, right? However, they weren't overt, they weren't obvious, right? But once you have the timing, early morning, June 30th, 1908, you can look and you can see, there are fingerprints of other things that happened, like a pressure pulse that passed over newly installed barographs in the British Isles and went around the entire planet twice. And based upon the velocity of that pressure pulse, we're able to back it up in time and see that the time correlated almost exactly with the Tunguska airburst, which created a pressure wave that literally moved around the Earth. But here is the final thing we should say is that there is evidence in hand, compelling evidence, that sometimes airbursts, the airbursts are not always limited to single events. Just like what we're looking at here with the Louisiana event, it's probable that that was one of multiple airbursts, perhaps even hundreds or thousands of airbursts that afflicted the planet at the lower Younger Dryas boundary. And if it turns out the Carolina Bays are the consequence of airburst phenomena, then that would also imply that there were thousands of airbursts occurring during the Younger Dryas boundary, if the dating correlates. But that would certainly explain the graph we looked at, where we saw almost the complete erasure of of Clovis cultural sites, Clovis occupation of the eastern United States during the Younger Dryas interval. So I would say the takeaway, again, this is just more of the constantly accumulating evidence that we are cosmically vulnerable. And we need to be paying attention to the bigger picture of which we are a part. But we're so distracted over this, because of this Malthusian worldview, that our human civilization is limited to the resources of planet Earth, that we're going to go down as a civilization fighting over a dwindling, finite supply of resources when we don't need to. If we just begin to really undertake what I think is the inevitable evolution to become a cosmic civilization, which we will be able to do two things simultaneously. One, we will be able to much more effectively create a planetary defense system, and also we will begin to harvest the resources, both energy resources and material resources of space. However, we need to get past this thing that's going on right now, because we're in a dangerous time right now. We have to recognize that. We talk about catastrophes. I call myself a catastrophist. I look at catastrophes throughout the history of this planet. And most of what I look at is catastrophes of a natural kind. But we could be facing a catastrophe of a human-made kind, if we don't get these conflicts under control, and soon. So I just, whatever it takes to get people to wake up and realize that, no, there's an alternate path. We don't need to go down this road of perpetual conflict, competing for a dwindling supply of resources. We need to really change our thinking. So that is something that I really hope and pray that we get through this time, because this is probably the most dangerous time since early 60s, when we were going toe-to-toe with the Soviet Empire, like during the Cuban Missile Crisis. And we managed to, come through there by the skin of our teeth, even though we claimed this close. What saved our asses was high-level diplomacy, talking, communicating, discussion, negotiations. We have to have that, and we have to demand it from our leaders. And I think Donald Trump needs to have his feet held to the fire, because virtually everybody that I know personally voted for Donald Trump on the basis of the fact that he was portraying himself as a peace candidate, and he was going to end the war in Ukraine. And he hasn't done that. And he's now looking like he's ramping up another war. And who knows where this is going to go. But I've got to be optimistic and believe that we're going to come through this ultimately unscathed. But there's so many variables here, and we know that these are the kinds of events and kinds of things that can rapidly spiral out of human control. So, I mean, it's coming down on, America's got to wake up and say, no, we're not going to, this is not sustainable, which it isn't. So that's part of the takeaway as well. So let's reconvene soon with another episode. I think that will have to be after the Cosmic Summit, which is coming up this coming weekend. And I think there's going to be a lot of great knowledge and information exchange there. A network is growing worldwide of people who are looking at these kinds of things, learning about these things, studying, researching, etc. This is also a very important thing that needs to go on, because, hey, we could go to war with the Russians over, dwindling resources in Ukraine, or we could form a joint venture with the Russians and the Chinese to build a planetary defense system and a lunar outpost on the moon, from which we could use as a base to begin to explore, colonize, and reap the infinite riches of the solar system. So I'd rather go that direction.
Same here.
And one of the things that's holding us up is just general cynicism on the part of too many people who just, are dismissive of these possibilities. But when you look at the big picture, no, I don't think that it's pie in the sky. It's not something that's just out of our reach. I think we can do it. It's just, do we have the will? Do we have the motive? Do we have the inspiration? And with those things, I think we can do it. And believe me, I would way rather be working together internationally towards those goals than the kinds of things we now see going on. So on that note, I guess we'll disperse. I'll go to the Cosmic Summit, be back next week. We'll record another episode. We'll be looking further at this. There's the whole history of this Younger Dryas controversy is super interesting. And we'll provide links and all kinds of things for people who want to do their own independent research. Because the more brains and minds we get on this, the more productive I think that our research will be.
Indeed. See you soon.
All right, John. Adios, my friend.